So good day everyone. So today we're going to discuss our topic. So first, number one is the course, which is the Mtec 102 or the Enhancement for Maritime course. Period, we are now in the final period. Week 1, this is the session 1, and the topic that we're going to discuss or report is the parts and errors of sextant and correcting perpendicularity error. And we are the group 1 and the members are namely, so yours truly, I'm the Cadet Religion G. Abad, together with my colleague, the Cadet Abajo Carl James, the Cadet Awali Paul Jandri, and lastly, the Cadet Tangkay George Neven. So for the course outcome, so is to know the basic parts and the purpose of the marine sextant. Second is to determine the types of the errors occurring in a sextant from correctable and non-correctable errors. And lastly is to correct the different perpendicularity error in the sextant. So for the learning outcome, at the end of this lesson, the student should be able to identify the parts of the sextant and understand how sextant works. Second is to determine the different errors in sextant occur. And lastly is to determine the perpendicularity error and corrections and apply them into a sextant altitudes. So for the importance of the topic, so as a future navigator or officer, it is very important that we know the parts of the sextant, the errors, and how to correct it as part of our course in order to measure the altitudes of the horizon and celestial bodies, especially if we are transiting in an open sea and no object or land can be seen, even if it's old tradition, but it is still applicable nowadays as an aid of navigation.
A sextant is an instrument for measuring the altitude of a celestial body above the Earth's horizon in terms of the included angle. By noting the exact time of such an observation and by referring to the nautical almanac, the line of position of the observer can be established. Two or more such observations of different celestial bodies or of the same body in different positions lead to a definite fix of position. A sextant can also be used for measuring horizontal angles. The basic parts of a marine sextant consists of the frame, the index arm, the index mirror, the horizontal mirror, the telescope or prismatic monocle, and lastly is the micrometer drum. So first is the frame. The frame of a sextant is either of rigid metal construction or molded plastic. It incorporates three legs upon which the sextant rests when in the horizontal position. The upper side of the frame is referred to as the plane of the instrument. The curved lower part of the frame is referred to as the lower limb of the instrument. The next one is the index arm. The index arm is mounted on a circular base plate and is free to rotate on a central axis underneath the index mirror. The arrow of the index arm is known as the index mark. The third one is the index mirror. The index mirror is rectangular in shape and set in a frame attached to the movable index arm. When properly adjusted, it should be perpendicular to the plane of the instrument. Its purpose is to reflect light to the horizon mirror. And the horizon mirror receives the image from the index mirror and reflects it back to the observer through the telescope. It can be either a rectangular or circular mirror held in an appropriate frame. As the horizon mirror occupies only half of the space enclosed by its frame, the observer is able to see both the reflected image and the horizon at the same time. Like the index mirror, it needs to be perpendicular to the plane of the instrument and parallel to the index mirror when the index arm is set to 0. Next is the telescope or prismatic monocle. This is used to enlarge the observed object and to make accurate observations easier. Higher magnification is desirable in observing vertical sextant angles of distant shore objects to obtain a clearer view of the sun's lower limb when taking sights. A wide field of view is important in trying to locate stars which are not easily found because of the apparent size. And lastly is the micrometer drum. While whole degrees are read directly from the arc, minutes of arc are read from the micrometer drum. Turning the micrometer drum screws the worm along the rack and permits fine adjustment of an observed angle or altitude.
So now let's move to the sextant errors. So the sextant errors has categorized to two, the correctable and non-correctable. So for correctable errors, we have perpendicularity error, side error, and index error. For non-correctable, we have collimination error, centering error, prismatic error, shade error, graduation error, and prismatic error. So for the perpendicularity errors, in a sextant, perpendicularity error is caused when the index mirror is not perpendicular to the plane of the instrument. So in the index mirror is mounted in the end of the index arm. To take the measurements with the sextant, you move the index arm, which is turned and moves at the index mirror. The graduations of the arc of the sextant measure the angle that you have moved to the index arm, and the mirror to the index mirror, which is fixed to the index arm. So next is the side error. In the sextant, the side error is caused when the horizon of the mirror is not perpendicular to the plane of the instrument. So, the horizon mirror frame is mounted rigidly to the frame of the sextant within the horizon mirror frame. The mirror itself can be moved and adjusted into through screws. When it is perfectly adjusted, it can create two errors, side error and the index error. The side error is the part we deal that within the step. It is the part created when the mirror isn't perpendicular on the plane of the sextant, and the horizon of the mirror is the one that you look through to see the horizon. In the index, next is the index error. So in the sextant, index error is caused when the horizon mirror is not parallel to the index mirror when the instrument is set at 0 degrees. When an instrument is at 0 degrees, the horizon mirror and the index mirror should show the same image. If both are looking at the horizon, it should be perfectly in line. We introduce the concept of the index error while we are correcting the side error and eliminating the correctable elements of it. Once we finish eliminating the side error, we accept the residual separation of the horizon as index error. The reason that we accept the last bit of index error is that we can account for it mathematically, or our iterative process before it's already taken out that we can. So the final index error correction is just getting the precise measurement of what is left.
Non-correctable sextant errors. Once your sextant is adjusted as well as possible for perpendicularity, side and index error, you are just left with non-correctable errors. Non-correctable errors usually result from the manufacturing process. They cover things to do with physical construction of the instrument, rather than accounting for each other separately. Manufacturers just refer to them together as the instrument error. This total instrument error is determined during calibration, completed before you purchase the sextant. You will be told the instrument error when you receive your sextant. Usually, there is a calibration card in the sextant box. The calibration card tells you the total non-correctable errors that you can expect from your sextant. Usually at low values, the errors will be negligible. Instrument error becomes more significant when the sextant reaches its more extreme settings. To correct for instrument error, you just apply the correction that the calibration certificate tells you to. In the case above, when taking reading above 97.5 degrees, you would add on 0.1 seconds to each reading. Collimation error. In the sextant, collimation error is caused when the telescope is not parallel to the frame of the instrument. You may also hear collimation error referred to as telescope error. Whatever name is used is just referred to errors in the mounting of the telescope on the main frame of the sextant. On older sextant, you would get screws to adjust the telescope, which allowed you to apply corrections for collimation. Modern sextants often do not come with these screws, which is why I now count collimation as non-adjustable error. When telescope is not parallel to the frame of the instrument, the light's path will bend slightly as it is reflected in the horizon mirror. Then again, in the index mirror, this bending becomes more significant as the index arm measures higher altitudes. Put simply, the greater angle you measure, the greater the impact from collimation. Fortunately, modern manufacturer techniques have pretty much eliminated collimation at smaller angles. The telescope is rigidly fixed to the frame of the instrument, so there is no need to adjust for collimation. Additionally, the angles that are most useful for navigating are unlikely to be affected too much anyway. Sintering error. In a sextant, sintering error is caused when the pivot point of the index is not perfectly aligned with the geometric center of the arc of the instrument frame. There is no definite way that the error will affect the sextant, so it is not possible to say that its angle will be greater or lesser due to sintering error. As it is non-adjustable, it will have measured during calibration and effectively eliminated. The main concept to remember with sintering error is that if the index arm feels slightly loose, sintering error will be present and will impact your readings in an unpredictable way. To prevent sintering error, it is important to take care of the sextant. Any impact of damage will prevent the bearings in the index arm from keeping it perfectly centered the geometric center of the frame's arc. Prismatic error. In a sextant, prismatic error is caused when the faces of the mirrors are not parallel to each other. A mirror is just a piece of glass that has been silvered on one side. When a beam of light hits the mirror straight on, it is reflected straight back. If the beam hits a mirror at an angle, it is still reflected straight back. But there is also a little refraction due to the refractive index of the glass. If the surface of the glass is completely parallel front and back, the refraction of the light enters the mirror is the same as refraction when the light leaves the mirror. They cancel out. If the front and back of the mirror are not parallel, the light is refracted slightly differently on the inbound path compared to its outbound path. The result is there will be a small difference between the angle of incidence and the angle of reflection. Modern manufacturing techniques mean that the mirrors can be produced with parallel faces. If the faces are not parallel, they can project a new mirrors made. Prismatic error is checked during the commissioning and calibration of sextant, so you can effectively ignore it on the sextant. On antique sextant, however, prismatic error can start become significant. Glass behaves like the incredibly viscous fluid, so over the surfaces can move. It can also have an impact of the viscosity of the glass in the mirrors. Physicals, as the warmer the glass becomes, the more fluids becomes. Over time, a warm mirror will deform more than a cold mirror. Overall, we just need to remember that prismatic errors will creep in over time. The warmer the sextant is, the quicker those errors will creep in. The typical lifetime of sextant, however, the small differences are not going to be significant. Shade error. In a sextant, shade error is caused when the faces of the shades are not parallel to each other and perpendicular to the plane of the instrument. The shades are designed to be perpendicular to the plane of the instrument so that the light passes through them normally. You want the light to enter the shade at 90 degrees, pass right through, and exit at 90 degrees. Any other angle will result in a small amount of refraction, introducing small errors in the position of image of the mirrors as there are multiple shades. This has the effect of multiplying any errors. Again, shade errors should be minimized during the manufacturing process. Over time, however, the bearings on the shades may become worn or damaged, resulting in that them in sitting correctly. When this happens, shade error is likely to creep in. The same as centering error, it is important to look after your sextant. The better it's secured for, the longer it will last before this error start becomes significant. Graduation error. In sextant, graduation error is caused by imperfections in the aggregation of micrometer of the markings of instrument arm. The sextant needs graduation so that you can read the angle that you have set the index arm to calibrate it so that it actually read double the angle that you have set the alarm to because the sextant works on principle of double. The graduation actually tell you the altitude of the body. You are ensuring that you don't need to extra mathematics result. If there are any errors in those graduation, however, it will present as error in the angle measure. The graduation should have been applied correctly during the manufacture and checked during calibration. There is no way for you to adjust on what is printed or engraved on the surface of the instrument. Worm and rack error. In a sextant, worm and rack error is caused by imperfections in the mechanism that hold index arm in position. The worm is screw that you turn to move the index arm, and the rack is a teeth along the arc of the sextant. The worm slowly moves along the rack as you turn the micrometer drum. As the gearing mechanism wears over time, the small errors can create no work on rack. You cannot correct for this, but it's possible to check whether they are present. Any sign of play or resistance in the gearing of arm will be sign work rack will be present as significant. The sextant arm should be fixed and not wiggle around when the worm is not moving. To prevent worm and rack errors developing, you need to take a good care of sextant. Ensure you apply grease and oil intervals specified by the manufacturer. When using the sextant, make sure the arm does not grind along the rack. If you are not moving the index arm, fully release the clamp before moving it. Then stop the arm completely before releasing the clamp. That's all for the errors of the sextant.
Thank you, Kukadet. So now let's proceed on correcting the sextant errors. So first, correcting perpendicularity error on a sextant. So begin by halfway extending the index arm. The temperature should be between 30 degrees and 70 degrees. Turn the sextant on its back and look at the arc with the arm set. Verify that the through and reflected arcs are identical. They will either be continuous, indicating no perpendicularity error, or have a step, indicating the presence of perpendicularity error. This image of a sextant checking for perpendicularity error. Notice the apparent step in the image in the index mirror. This means perpendicular error is present. If your inspections indicate a perpendicularity issue or error, you'll need to adjust the screw on the index mirror's side. On the index mirror, there is generally only one screw, so you only have to turn that one. Continue to compare the picture in the index mirror with the real arc while adjusting the screw. You have removed as much perpendicularity error as possible after they are in line, appearing as a continuous curve. The index mirror becomes perpendicular to the instrument's plane with the perpendicularity mistake is removed. So now let's proceed to correcting side error on a sextant. So it is an iterative technique to correct a side mistake or a side error of a sextant. You incur a little index mistake when you adjust for side error. Similarly, changing screws to rectify index mistake introduce a little amount of side error. This step's purpose is to minimize side error. Set the sextant to 0 degrees and stare towards the horizon to get started. Tilt your head 45 degrees right and staring towards the horizon. There will be a horizon step if side error is present. For sample reasons, I've included a lot of side error in the above picture. It's possible that your horizon is only slightly off. The side error screw on the side of the horizon mirror is adjusted to eliminate this side error. this screw seems to be on the top when you tilt your head. Continue to use the sextant to align that horizon. So you may now return your head back to its original position. You will next be given one of two options: either the horizon is still straight or it isn't. If it's in line, you have to remove all sextant mistakes or errors. More than likely, the horizon has moved forward. If you've made an index error, you'll need to adjust the index error screw in the horizon mirror. Continue to stare through the sextant until the horizon lines up again. After aligning the horizon with the index error screw, tilt your head back to 45 degrees while correcting for the index error. You're now checking to see whether you have caused any additional side errors. This is the iterative correction technique for side error. You alternate between adjusting both screws while moving the sextant between vertical and 45 degrees. When you have eliminated as much error as possible, use the side error screw to make your final 45 degrees fix. Side error must be removed, as you can account for the final bit of index error in the next stage. Let's move on for the correcting index on a sextant. So to fix an index error, you must first determine whether it exists or not. Set the sextant to 0 degrees and then concentrate on a distant object. The horizon is just right. The sextant has no index error if the horizon seems to be continuous. Index error is present if there is a step in the horizon. Next illustration, the index arm of the sextant is set correctly, giving you a continuous horizon. Your index arm is in the right position for reading off the index error when the horizon is continuous. This is your index error. You read what the sextant's micrometer drum is set to. There are two aspects to the index error. You've got the absolute value and the direction. We examine if the reading is on or off the arc to determine the direction. So there are two directions, on or off the arc. When a reading is on the arc, it signifies you've moved on the graduations, just like when measuring a star's height. When a reading is off the arc, it signifies you've deviated from the standard graduations, which is equivalent to measuring an altitude below the horizons. So in this illustration of on the arc and off the arc. An index error of the arc must be added to the measurement when making adjustments. The sextant's 0 degrees setting is a little farther back than the graduations show. An index error on the arc, on the other hand, would be applied the other way around. All of your readings would be reduced by mistake. That's all for our group presentation. Thank you for listening.